have like a good, knowledge about, what it would be like to have an internship at like a, NSTDA. Like one example. Thank you.
You're ready.
Yeah, it's already started recording.
So, good morning. This is my final internship presentation. I was an intern for 7 weeks at MTEC NASDA. And this is the brief timeline of what I did during my 7 weeks here. So for the first week, I was onboarding about the task and introduced the software I had to use here. And each week I have to read some articles about the related study. And in the second week, I started exploring the software. And in the next week, I started to collect data on that software. And on week 4, I continue collecting data on that software and then introduced one more Lex machine, which is a laser scanning microscope to collect data as well. On week 5, I continue collecting data on both machine and software, and then started a little bit of data analysis with some of the collected data. And in week 6, I finished up my data analysis, and on week 7, I prepared my final internship report and this presentation. So, and this is the software and machine used during my internship project. The first one is called the purple one, Simpleware. It is like a software that we have to use, like that is used for 3D image processing. So it can like visualize 3D image data. And the second one is called Lex. I'm not sure about the model number, but it's a laser scanning microscope which has many like microscopes lens. Yeah. And then for the first part, Simpleware, this is a step example of how I had to like collect the data. Like first I was given some picture of this black circle one. It is a picture of the metal which was scanned, and I have to import it, and then there's a voxel size of 0.33373 millimeter, and then had to create mask for each face, and this is the steps that I have to use in that software. So, and yeah, and then for the third step, there is I had to like differentiate the grayscale in order to know which face is which color. So there were 3 faces, like porous, ceramics, and metal. So, and then after I differentiate, I apply some filter to make it look more nice, and then the right hand side is some of the effects that I used. And then in number 5, I found volume fraction for each face, and then the answer is in percent. And then after that, the last one is label the pores, like which face is like how big in differentiating colors. So yeah, this is the steps. And then so like what I have to do was so to like modify some of the properties of the metal, like less weight. So I heard like the ceramics were poured into the metal, so which the ceramics would sink and make big chunks. So in order to remove them, I had to like make the model into many cuts and find which part is the like accumulation of some white chunks. So this is the I made like 9 cuts here, and each cut is 20 micron wide. And if you can see here, the blue plate, maybe the fourth one, there's like a white chunk there, which is the ceramics chunk. Like, so it's not good for the metal. So, and then for example, like on the 8 or 9 cut, there is no white chunk to be seen. So as you can see in the graph, like on the right hand side, the first blue line is the pour metal, and the middle gray line is the ceramics, and the lower line is the porous. So it's based on the volume fraction, and it can be clearly seen that on the fourth one, the 13.4% of the gray color is really high. So that's like the biggest ceramics chunk there. And as the cut go lower, the ceramics was nowhere to be seen, like almost 0%. And yeah, and then this is the raw data that I got from Lex machine, the microscope machine. There were 27 samples, like with different some of the metals were tested with different power, different laser power, different laser speed, different hatch space, and these are some of the surface roughness parameters that I got, and the rightmost 3 were the independent variables. And I with that date, I did ANOVA analysis, and then I found out that with ANOVA, it's the p-value is really less, which is really low, the yellow one, and it means it's a good p-value because it's less than the 0.05. And then I also did correlation. And then there's like, so we can only look at the last 3 rows, and because the first rows were like the relationship between each surface roughness, so that doesn't matter. So the if we look at power and SSK, there's the which I highlighted yellow. That is good because it is like positive, like greater than 0. So in correlation, like if it's correlation exists only between -1 to 1, and if it's greater than 0, it has a relation. So I highlighted the ones that has a good relationship with power, speed, and hatch. So in conclusion, like on the below, power and SSK, speed is good with everything except SSK, but hatch is like good with only 3 of them. And then also I did simple regression analysis with that data. So first, I used simple regression for SA and power, the first picture, and the p-value is low, which is lower than 0.0001. This value of 0.0001 is found on the article 1. that I read like when I first came here. So I use that as a reference. And then for second one is with speed. That is 0.005. It is a little bit, I mean, a lot greater than my standard p-value. And the last picture at down is also 0.003, which is SA and the headspace. So from this three, only power is a good parameter for SA because of the lower p-value. And then this is the SZ. The first one is also like power, and second one is speed, and third is hatch. So this one as well, only power, because it is the other two, the value is greater than my standard 0.0001. And the third one is also this is SV. This one also with only power. And then yeah, and this is SKU. SKU is also SKU has a good relation with every 3 per meter. All of the p-values are really low. And then SSK also the same. Yeah, three of them are good parameters. And SQ, this one is only with power, and the other two are a bit greater p-value. So I summarized the p-values that I got for the 7 parameters. And so like for power, it can be seen that every parameter is can be used to like determine, and speed for only speed and hatch only SSK and SKU. And then I also did multiple regression analysis using MinTab, and for the first one, SQ, this is the regression equation, like which, for example, like the coefficients will be the value that how much it will have effect on, or it will change the value if the power changes or something like this. So the first one is a regression equation, and yeah, there are coefficients that we can put in that equation, and the model summary, like the R-square values. And what I want to mention here is the plot, the residual plot. So if you look at here, the second plot versus fifth plot, it is actually bouncing around 0. So and then the normal probability plot is it has a like trend line. And then yeah, that's what I want to talk about. And then for SSK, here's also the regression equation. Yeah, and then the R-square adjusted value is 23.17%. And then for the plot versus fit, this one is more like balancedly scattered near 0, like compared to the first one. And then for SKU, this versus fit plot, like they are like a group of three parts, 3 pattern parts. And for SP also something similar. And you can see some of the outliers here, like which is like maybe the one from the really above. It's not like in the group with the other data points. So, and then for SV also, it's very scattered. It goes really high up to like 100 or minus 50. And then for SC, this is the regression equation, and in the versus fit, it's like a vertical kind of trend. And then for SA also, this is the regression equation and other model summary and the residual plot. And then or if I have to explain the residual versus fit plot, like if this is to verify the assumption that the residuals are like randomly distributed and they have constant variance. So if the pattern is like fanning or uneven spreading, it can be indicated as non-constant variance, or like curvilinear, it can be interpreted into missing higher order term, or the point that is very far away from zero is called an outlier, and if if the point is far away from other point in the x direction, it is called influential point. So yeah, this is what I have prepared. So any question?
Thank you, Grace. That was good job on that. Thank you for your work for us. I have one question. So based on the R square values that you found from your regression analysis, what would you suggest? Like how would you suggest any of those parameters are affected by the independent variable?
You mean from my which regression, simple or
From your
multiple?
multiple, because you
Okay.
have different R squares between each independent variable, right? Between
Yes.
between each parameters, yeah.
Okay. Eight. Yeah, I kind of noted down here. The R square. You want to know about R square?
Yeah, explain a little bit more about R square and how should we analyze based on the data that you got.
Okay. So R square, like the value of R square increase when you add more data to a sample. Like it's like it's more useful when the data are same size. Yeah, data set is the same, and if the R square value is higher, the model, I mean, the better the model fit the data. Like have to be always between 0 and 100%. So the higher R square value means which is good. So if I have to look here, I think I think the second one is the highest R square value. This NSK, because it has like 32.03%, and the others are like running around 10 to 15.
Okay, but I think 30 is still too low for the R square value. It looks like there's no strong relationship between the parameters and the independent variables that we're using here. Is that right? Because I think 32 is not very high. I mean, at least supposed to be 90, right? to
like
have a good fit of the data and the regression equation?
I work maybe in it there is a value. Oh yeah, here in the oh, in the regression simple regression also, like there are R values if you can see here on the third line 0.0069. So for each also it has like their own R square value. So they're also like, I think this is low because it's separated like one each with each parameter.
But looking at the single regression analysis, you have a pretty good p-value for several combination of your variables, right? So
Yeah.
it looks like there's a stronger relationship between single independent variable to the parameters better than when you do the multiple regression. Is that right?
Yeah, I think so too. Because with simple regression, like power power has really like really good low p values for every
Mhm.
parameter.
Okay. Anyone else have any questions?
Can I? Can I?
Sure.
Okay, so right now I'm trying to understand your work. It's like your independent variables are the power, the speed, and then there's the point, right? So these are the three independent variables. And then you have
Yes.
like so many dependent variables, including those like S thing, yeah, okay.
Yeah.
And then do you think that all the S's are correlated among each other? Like, you know, the high SSK, I'm not sure the number, the alphabets, but like the high SSK also might impact, you know, SK or SU. Is that going to be the case, or do you think that they are like very totally independent?
I think they don't have a relationship between among
No.
themselves, like only with
Okay.
the parameter. I mean the
Okay,
independent
so then
parameter.
that's why you did your multiple regression, like for all the S's, you know,
Yes.
separately, right? Okay, and then just one. So these experiment data, did you generate it from, you know, like, I don't know, like decide experiments, uh, any
I
technique? Did you use any decide experiment technique, or did you just like, you know, collect any data that you could do based on, you know, the limited uh, machine or whatever time? Did you use any design experiment technique at all?
no, because I also refer from the articles that I read, and they mostly use these kind of analysis and the data because like collecting data itself like it was like more than 1 month, so because of the time limit also.
Okay. And then, so that just focus on the multiple regression results.
Okay.
Another one is that why didn't you put, you know, like more terms like power square, speed square, like quadratic term of all the parameters, or even the interactions among the parameters like power and speed, power and whatever. Like, why didn't you like consider the interaction between those parameters, or do you think those are not going to affect the result?
Do you mean power, like the
Yeah, like
relationship?
I don't know what software did you use to analyze this?
Multiple regression?
Yeah.
MinTab.
Okay, and like in Minitab, you can actually input like, quadratic term, even the power, the third power, the fourth power. You can go up to whatever number of power that you want. I think it would be interesting to add more terms, like the quadratic term of all the parameters, or maybe the third power of all the parameters, and also the interactions among them. And more to that, you can even use kind of like, it's like really easy click, like stepwise. And if you use stepwise, it's gonna delete the parameters that are not needed in the model, i.e. the parameters that make the model, having bad R square or worse R square or whatever. And then the final parameters would be the one that you can, discuss about the results. So I think adding just one parameter, just the power of one parameter without interaction might not be sufficient in this case. I'm not sure, maybe or may not be. And also, I think I want to comment a bit about the low R square. There are a lot of studies that have low R square. Pretty much those studies have very small sample data. So I think it's not, it's totally normal with this case, I would say. But I think the main ones that you can explore is like whether those parameters are significant statistically. And in terms of significance, why did you use the cutoff of like 0.00001 or whatever? It's so low.
I used it as a reference from the article that I read.
Really?
I
They
I
use it.
gave her
But
like a
for
paper to read. But
Okay.
you go back to your slide number 7. I mean, if you increase your 17, sorry, 17.
oh, then-
My bad. So I'm
So
trying to
yeah, it
see.
seems here, yeah. Go ahead, sorry.
Yeah, I'm trying to see like if you usually the p-value is higher than that, right? And is it like 0.005 if I'm not wrong?
Yes, like conventionally,
Okay.
people use 95% confidence level, so that should be, 0.05. Any p-values below 0.05, you assume that those are significant statistically with 95% confidence level. But this is not a cutoff or anything. Like sometimes if you are curious, you can go to 90%, like 0.1, depending on the results, and you can conclude your results based on the results that you have, and
Yeah,
based
I
on the
think
level of confidence. Yeah.
yeah, I think
So from
95% confident is good.
goodใช่ไหมคะ? Yeah, it seems like from this table, all the parameters are significant
Yeah.
for like just the single run, right? So you use like 1-to-1.
yes.
Yep.
Yeah, so I think this result is like doesn't really tell much, for me, I feel like. But maybe, if you could add more terms in the multiple regression, you might see something, or even the interaction terms. Okay.
Would it take long to run more multiple regression analysis?
No.
Okay, because I know you have to go to the embassy today, right?
It's okay. I rescheduled to be on Monday.
Oh, okay, great.
โอเคค่ะ
Yeah, so if you don't mind, you can.
เดี๋ยวแป๊บนึง
Yeah.
นะคะ If you have any question running the model, you can talk to me later on.
Okay.
Okay, so this is good. Gong and Bab, do you have any questions? We're running out of time. We have 10 more minutes.
No, I don't
I
have.
I have a little question about this table and the multiple regression that you do. Is it the same result? I mean, the same trend about
It's
the parameter that affect the SK, SQ or anything? Is this
Mhm.
it show the same trend of results?
The first one is like analyzed using one of them, and so it's not quite the same. And I also didn't use the same p-value. Like for example, I used 0.001, but uh, the multiple regression, I just used 95%.
Mm-hmm.
So it would be quite different.
I see. Okay.
So,
I have
uh,
one more question.
mm, do you have?
No.
Okay. Uh, Given this data and your analysis, okay, let's say I or some of your customers have has some problem that he would like to uh, let's say optimize one of these S parameters. Let's say SP or no SSK or something that is peak height. He want to reduce it. What is your suggestion and why?
Mm, If he wants to reduce the SSK, we
Yes.
can look at the power, the three of them, power, speed, and hatch. I think we can like maybe um, decrease them because all three of the parameters are have some effect on this parameter. So for example, for other SQ or something, we can just play around with power as they are, yeah, some relationship.
Okay. So based on what we see on this table, uh, you means the power has the most significant
Yes,
effect on the result, right? We should begin
yes,
with the power first.
yes.
Okay. Uh, can we only or should we only rely on or look at the p-value, or what what kind of consideration can come in handy? Just discussion.
P-value and I think if you want to look, you can look at the R-square values or R-square adjusted values. Yeah, P-value, but P-value is like the main one.
Okay. It's okay. Thank you.
Okay, so if there's no other questions, I suggest, Grace, can you please do more multiple regression analysis, just like Ajahn Jeff
Okay.
suggested, and just send us the result and also the Minitab file.
Okay.
นิดนึงค่ะ
Sure.
to comment on กล้องใช่ไหมกล้อง question ค่ะ actually if you had like a pretty good design, you know, there are several design experiments techniques that you can use, and you know many of them can be used to design in such a way that you can later on, you know, fit a function and then, you know, try to find what's the value of like the optimal value of the power, speed, or hatch that, you know, optimize those Y's like SQ, SSK, SKU, whatever. You can even also do that. But I think a better designs can help a better result in that case. From this data, I'm not sure even you know fit like a quadratic term or the power of 3 term or whatever. I'm not sure if you're gonna get you know a pretty good optimal value for these you know power, speed, and hatch. But you can later on you know do another design and then try to find the optimal one.
Well, these samples was made in Japan. So what we did was we did the full factorial, and they just like run all of the parameter combinations, and this is all we get. And it's gonna be a little bit trickier to get more samples. But in the future, if we have to do more experiment with them, maybe we'll ask for some of your interns or your students to help us on the experimental design.
Next year, please. Thank you. Okay.
Okay, I think this is good.
Okay.
So, Grace, and I will work on the payment for you. It's gonna be very, very difficult, but I will try my best. And I also get an email from your staff in Gazette asking for the assessment, and I will send that back to her today.
Thank you.
Yeah, and thank you for your work with us.
Thank you so much.
So don't forget to send us the data later
Okay.
today. All right. And good luck with your exchange in Sweden.
Thank you.
Yes, good luck.
Yeah.
Thank you.
And thank you อาจารย์เจี๊ยบมากค่ะ
Bye ค่ะ
จ้าบ๊ายบายค่ะ
สวัสดีค่ะ
Bye.
Okay, thank you very much.
Thank you.
See you later. Okay, stay healthy. Bye bye.
Bye.
Bye. Stay safe.